All right, so welcome back. Remember that on Monday we won't have class, of course, and we also won't have any help hours on Monday because of the Labor Day weekend. And so make your plans accordingly. We'll still have help hours on Tuesday before your first hack is due. So if you're not done with that, make sure that you get into help hours. I guess not help hours, but lab hours on that Tuesday, that you can go and ask questions about the hack if you need to. But otherwise, to pick it up where we left off, we were talking about types of variables. Now, there are more types of variables that we're going to talk about than these three, but we'll leave those for later. We're going to be primarily using integers, doubles, and characters. The characters are going to be single characters, right? And we left it off with looking at the ASCII text table, where a character is basically a number, right? Because if you have uppercase A, that has a number 65. If you have a space, that's number 32, right? Because at the end of the day, in a computer, computers don't understand English. They don't understand A, B, C, D, right? They only understand zeros and ones. And so at the end of the day, everything has to be represented by a number, either a 0 or 1 or a collection of those things, okay? All right, so when you, there are limitations again, but when you create your own variables, you have to give them names, right? So there are some good practices when you are naming your variables. There are also rules, and some of the rules are that they can't have spaces. They shouldn't contain weird characters, that is Unicode, no hyphens, et cetera, et cetera. Hyphens are not allowed because a hyphen is a minus sign, and so you'd have variable minus variable. That's how it would interpret it. It cannot begin with a number and should not have any numbers, all right? So cannot means that it's a rule. If I tried to create a variable 57 hello, right, then it would not be interpreted as a number. You should not have numbers. That's a guideline. Hello 52, right? That would not be a good variable name, right? In fact, some other terrible variable names would include very short variable names like X, Y, A, B, right? Variable 1, variable 2. I need another one, so variable 3. Those are terrible variable names. They're valid, right? And you can use them as far as C is concerned, but they're terrible variable names. Some variable names that you'll see as you go along are placeholder variable names like foo, bar, and baz. These are just programmer tricks that are conventions that if they need to demonstrate some code and they don't know what the variable is standing for, but here's how you create a variable, my placeholder is going to be foo, right? Or if you need two of them, bar, and then a third one would be baz. They have no meaning, right? I mean, if you know what foo bar is, then you know what the meaning here is. But baz has no meaning, right? When you are writing your own variable names, be descriptive, right? An example would be the number of students, right? Number of students tells you exactly what it is modeling, right? If you are doing something mathematical, right, and you're writing a function and there's just X, fine, maybe that's the only thing that's appropriate. Or maybe A, if it's like a coefficient to a quadratic equation or something, right? Those may be okay variable names, but really think, is there a better way of doing this, right? Another example would be in our program. Is KMS a good variable name? Right? My answer would be it's probably good enough, right? Now, in the context of our program, remember this program over here is converting from miles to kilometers. Miles is pretty self-descriptive. If I just said M, all right, here, let's go ahead and go M. Is that a good name to represent miles? Terrible. Why? What does M usually stand for? Meters, something completely different. Mile? That's a better variable name, but is it ideal? It's 1 mile, right? Miles is the best variable name there. Now, in contrast, KMS. If I took the same track, I should have used kilometers, right? That would have been better instead of this abbreviation. But in the context, this is probably okay. This is probably good enough, right? Always look for, the bare minimum is good enough, but you should strive for the best variable name possible, right? Avoid ambiguous abbreviations, right? Like I just did, KMS, well, there's nothing really else for KMS, kilometers per second maybe, but that's KPS, right? Yeah, go ahead.
If I just use like kilometers
That's a good. It's always going to be the Goldilocks zone, right? Not too hot, not too cold, not too long, not too short, just right, right? And that's why I say, is it good enough? Because once you're in that Goldilocks zone, then you're probably good enough and just move on. But there are variable names that can get way too long, like kilometers per hour in a quantum system, assuming whatever. That's way too long, right? Something like that. But KMS is probably good enough within the context, as long as the context says so. For example, you should avoid some ambiguous abbreviations, right? What about Social Security, SSNs? I already gave it away. What does SSN stand for? What does that likely stand for? Social Security now. Likely, good enough. Good enough. Enough, right? But what if I did this? EIDR. EIDR, there we go. Does anybody know what that is? Maybe if you knew what it was, but not many people are going to know what that is. That's an now I don't even remember what it is. It's like an ISBN, but it's for all media. So movies get their own EIDR. Television episodes get their own EIDRs, right? And only if you knew it and you were within that context does it make any sense. So EIDR is probably not, unless there is context. So generally avoid abbreviations. You are not being paid by the character, and you're not paying by the character. It's not 1979 anymore where, instead of writing square root, right, we write SQRT instead. Because when we save a byte here and then we save it in 20 different places, it mattered back in the 1970s, right? It doesn't matter anymore, right? You're not paying by the character. Overall, just use a consistent naming convention. Our recommendation is to use what is called lower camel casing. This is also called lower snake casing for variables, for all variables, right? This is the modern convention. And it's what I'm going to recommend that you do, because there's an old school convention that uses lower camel casing. Lower underscore casing, right? In fact, it took me a lot longer to write that one. Why did it take me a lot longer to write that one? Because I had to put my pinky on the shift key, go all the way across the keyboard to the underscore in order to separate out that word. Save your pinkies, right? And save on typing by using a modern lower camel casing convention. The idea here is that if you have compound words, everything is lowercase except for the first character of each subsequent word, right? Not the first one. That's still also lowercase. That's why it's called lower camel casing. All right, and it's called camel casing because the capitals form humps like a camel, right? Lower underscore casing, that's hopefully self-explanatory. You're using these underscores to separate words. You can also have upper camel casing, and a lot of other languages use this. For example, Java uses this for their for classes. Later on, when we do enumerations and structures in C, we will use this upper camel casing. The only difference is that the first word is also uppercased on its first letter. Right? And also, you can use upper underscore is one word, sorry, casing. Where have we seen this already? You remember? Constants, m_pi, m_e, right? In other words, this is used for constants, right? Or macros. Right? I did this also in our program over here. KMS per mile, because it was a constant, it's not going to change, right? Even though it's technically not a constant, it's a macro. I made sure that it was all upper underscore casing so that you know that this is a constant right here, KMS per mile. Right? So be consistent above everything. If you want to go with an underscore casing, fine. Your pinky will drop off by the end of the semester, but be consistent about it. Don't use underscore casing on line 5 and then below use lower camel casing on line 10. Right? Variable names generally should be nouns. Right? We've got this whole analogy with writing English. We've got paragraphs, we've got sentences, right? Well, we've also got punctuation. We've also got grammar. Nouns are things. People, places, things, right? And so that's what the variables are representing. number of students, for example, or interest rate or something like that, right? Those are all nouns. When we eventually get to functions, functions do things. What's the thing in English grammar that does things? Verbs, exactly. And so we will name those after verbs. But for now, just with variables, they should be nouns. Okay? What about the operators? Now we can jump down to line 19 here, where we were actually computing something. We took kilometers per mile, which was 1.6 something, and we multiplied it by the number of miles that we read in from the user. This is our multiplication operator, right? And we have these basic operators, right? For example, we have addition, subtraction, and multiplication, like I already just said, and we have division, right? I should have said division, so I should need to put in division there. Division, right? Now, addition and subtraction, those are pretty straightforward, right? They're on your keyboard. But the keyboard predates modern computing by 50 or 100 years. Look everywhere on a standard QWERTY keyboard, and you will not find that X right there that denotes multiplication. You will not find the centered dot there, nor will you find this thing, right, that's used in grade school with the horizontal line with the two dots, one above and one below, right? You will not find those in the QWERTY keyboard. So what we have to do is we have to use something that looks kind of like it. And for multiplication, that's going to be the star or the asterisk. We can't use X because X is a character, and that would be used for a variable, not an operator, right? Likewise, we can't write A over B with a line through it, right? So the most appropriate thing that we can do is approximate that by writing A divided by B, okay? All right, what other operator do you see in this one line here? We're definitely doing multiplication, but what this is that's a variable. This is a macro. This is a variable. This is an operator. The only thing remaining is, what is this thing? It's called the assignment operator, right? Variables hold values, and you need a way to put those values into the variables. To do this, you use the assignment operator. The assignment operator is a single equal sign. Now, why was it like this? Well, it was a bad decision 50, 60 years ago or whatever, whoever started it, maybe Fortran or something, I forget. But they made a bad decision and decided to use the single equals operator, which meant something completely different in algebra. If you were to read this in algebra, what would it be? The thing on the left-hand side is equal to the thing on the right-hand side. That's not an operation. That's an assertion of truth. Is A equal to B, or is A not equal to B, right? But that's not how they ended up doing it in programming, right? Some programming languages did recognize that this is a stupid idea, and they instead use colon equals. Maple and I think maybe COBOL or Fortran or something like that. There's a nice programming language called Haskell that does what, or has a symbol that does what it does, right? Take the thing on the left-hand side and then arrow, put it in the thing on the left-hand side, right? None of those languages are in super wide use, though. So almost every single programming language uses the single equals operator because of some mistakes 60 years ago, right? So you use the single equals operator. It is not an equal sign, right? It is not algebra. This is not algebra, right? It is not an equal sign in algebra. Instead, again, it means take the thing on the right-hand side, or take the value of the thing on the, right-hand side. I've got that wrong. Right-hand side, right? Right-hand side, and place it into the variable on the left-hand side, LHS, right? There we go. It only ever works like that. The variable that you're assigning is never on the right-hand side, and the left-hand side can only ever be a variable. If I did something like this, KMS times 2 is equal to that, right? Then I'm going to have a syntax error, and GCC will not understand what I'm talking about, right? There, the L value, that is the left value, required as the left operand of an assignment. It's kind of cryptic, but if you ask, the rubber duck debugger here, what this actually means, it's going to tell you that you can't do something on like this on the left-hand side. Right? Go back over here. Right? So, but anything goes on the right-hand side. It could be a single value, right? The left-hand side, the right-hand side can be a variable, a value, an expression, etc. So, for example, let's go into code mode just in here. I can create a variable a and immediately set it equal to 10, right? Later on in the program, I can say, well, now I'm going to change it. Because it's a variable, it can vary. I'll set it to equal to 120, right? The thing on the right-hand side could be another variable. So if I go int b is equal to a plus 10, right? That's an expression, actually. Let me simplify that. Let's go with b is equal to a. All I'm doing is taking the value stored in a, and I'm copying it over to the variable b. If I have another variable here, I could say it's equal to b plus 10, and I'm simply just taking the value stored in b, adding 10 to it, and then placing the result into c. Right? You can get a lot more complex than that, and we will eventually. But otherwise, the left-hand side has to be a variable that you assign. The right-hand side can be a variable, an expression, or what we call a scalar. That's just a number. Okay. Guess what? Something that you're familiar with? PEMDAS rules. They apply. Remind me, what does PEMDAS stand for? Parentheses, exponents, multiplication, division, addition, and subtraction. Exactly. So therefore, the following are not, emphasize this, not equivalent. If I said, say, in code, a times b plus c, which one of those things gets evaluated first? A times b, and then we add c to the result. And this is not the same as if I did this. A times b plus c, because I'm putting them into parentheses. Now, parentheses have a higher order of precedence. So what happens? B plus c gets done first, and then it gets multiplied by a. So the same PEMDAS rules that you've been following in just algebra or arithmetic, actually, for your entire life, they apply here as well. Why? Because code should be familiar, right? We're trying to be as English as possible. Here's another example. What is that thing? That's the quadratic equation. How do we write that in C? So let me go ahead and create a variable to hold the first root, int, double, root 1 is equal to, right? All right, well, let's try negative b. How do I get a negative? Let's just type negative, right? Negative b, there we go. And then plus minus, can I do that? First of all, technically I can't even do that in math, right? Now, we write plus minus in math because we don't want to write out two equations, one with the plus and one with the minus. There are actually two equations here. There can't be two values to an equation, right? So we can't do this in code either. Let's just take one of them. Let's just take the plus. How do I get that square root? SQRT, good. B squared is b squared plus 4ac. Yeah, what is this thing right here? That's how I normally write it in, say, math or LaTeX or something like that, where I'm writing out, some algebra stuff. That will actually compile. That will work. It won't give you what you want because it's the exclusive OR operator. So, suggestions. Yeah, go ahead. Suggestion?
You can use the EXP.
Ah, okay. Well, EXP is for the base E. So, E raised to 2, right? I want B raised to 2. So there's something like that that's called POW, right? B raised to the power 2. But do we really need that? I mean, that's a very powerful tool, right? Do we really need that if it's just B squared? B times B. Right? That gets the job done. In fact, that's so straightforward that the compiler will do it for you. If it sees that you're raising POW to 2 or 3, it'll take your code and replace it with more efficient code that's just B times B or B times B times B for a cube. Yeah?
Would you need parentheses before you define it?
Yeah, we'll get to that. Yeah. But what about that 4AC first of all? Can I could. That's how I wrote it in math, right? Because implicitly no space means that you are multiplying these things together. There is no implicit there. We have to explicitly say times and times. Right? Yeah.
Yeah,
Oh, sorry. Thank you. All right, good. Now divided by 2a. Oh, no. 2 times a, that's even better. But is that still correct? Yeah, it needs parentheses. It needs parentheses in the denominator. And guess what? It also needs parentheses in the numerator. It doesn't cost you to write more parentheses, right? Parentheses are absolutely necessary in this case, right? But even in sometimes when it's not necessary, it's still a good idea to put them in to make your intention explicit. Right? What about that second root? Root 2, and then the only difference is minus instead of plus. Are those good variable names? They're not ideal, but they're good enough, right? Why are they good enough? What else would you call them? One's a root and the other one's the second root. First root, second root, okay. Root 1, root 2, that's just as good. And they both start with the same thing, right? So in some contexts where you're doing something mathematical or there just really is no better description, yeah, those are okay variable names, right? All right. Yeah.
When you do this, you had like 2 sets of parentheses. Would it matter if you had used a bracket instead?
Oh yeah, brackets are not like that, like a square bracket. Square brackets are not used in expressions; they are used in arrays. So yeah, you can't use square brackets like that. Right? That's used in a different context entirely. You also can't use curly brackets either, right? But then mathematicians don't either. Right? So some pitfalls here. When you add, subtract, or multiply 2 integers, the result is always an integer, both mathematically and in code. If I go 10 times 20, I'm going to get 200. That's still an integer, right? But also, when you divide an integer by an integer, the result is still an integer. That has some consequences. Let me come over to this demo code here and show you what the consequences are. Int a is equal to 10. Int b is equal to 20. Double c is equal to a divided by b. Printf, and we'll talk about formatting here in a little bit, or c is equal to %f and the line. What value will c have right now? Let's think this through. If this were math class, right, then we would say 10 divided by 20, that's 0.5, right, 1/2. But since it has to be an integer, what happens? 0.5, is that an integer? 0.5, that's not an integer. How do we make it an integer? By taking the non-integer part and throwing it away, resulting in 0. Right, so gcc demo.c and a.out. Oops. Looks like, oh, I'm editing hello, sorry. All right, let's go ahead and get rid of that, and let's open up demo. That's what we were working on last time. There we go. Try that again. There we go. So there is the result, 0.000. That's called truncation, right? And that is something that you need to be aware of. When 2 integers are divided by each other, the fractional part is thrown away. That's called truncation. It just gets truncated, right? 10 divided by 20 should be 0.5, but it ends up being 0.0. There is a way to solve this issue. First of all, you don't have to always use doubles, right? In fact, you shouldn't always use doubles. Integers are a very good thing. You can solve this by doing what's called typecasting. What I'm going to do is I'm going to take, I'll change this so that double. I'm putting a double inside parentheses here in front of the b. What that does is it says, oh, look, I know that a and b are both integers. For the purposes of this division right here, however, treat b like a double. Now an integer divided by a double is going to be a double. 0.5, that 0.5 is now preserved. So when I print it out on line 14 here, it's going to be preserved as 0.5. Right? I could do both if you want, but it's not necessary. You can go ahead and typecast a and b, or a instead of b, but at least one of them has to be typecast. Right? And again, it doesn't change that variable. It only changes it temporarily for the purposes of that expression. Right? Yeah?
Does C have to be a double?
Yes, because if we did that, then it doesn't matter about truncation now. In fact, yeah, it's giving me a warning about this, but it'll end up outputting 0. Yeah. Because when it gets assigned, truncation happens as well. So let me undo that. There we go. All right. Let's put that in the notes too. And you'll experience that in your lab on Tuesday next week. There we go. All right. So the solution is to do typecasting and just force one of them to become a double. There's some other pitfalls, right? Sometimes you have invalid operations. What is 1 divided by 0? Can you do that in math? Can you divide by 0? No. So what happens to your calculator when it happens? Error or something like that. What happens in calculus if you try to divide by 0 but using calc, where you're going 1 over x as x approaches 0? Shoots off into positive infinity. That happens here too, right? This might be maybe infinity or NaN. NaN. There we go. What's NaN? Not a number. Not a number times 5 is still not a number. Infinity plus 2 is still infinity. You're basically dead in the water at that point because you've got an arithmetic error and there's nothing that you can do to fix it, right? Let's see. What about square root of -1? What is that in math? I, right? It's an imaginary number. It's a complex number. This will result in NaN as well, not a number, because it only deals with it only deals with non-complex numbers. Here's another one. Pow of 0 to 0. That's a really good question. In mathematics, what happens when you raise 0 to 0? Well, you raise it to the power of 0, so obviously it has to be 1. Right? But then it's 0. How did you get 1 out of that? Right? It's an undefined behavior, right? It's undefined. What happens when you've got x to the power x and x approaches 0? That'd be a good question. Go ahead and graph that sometime. Right? What happens when you try to get to 0, x to the x? Well, we can do that. We've got time. What does x raised to the power x look like? Plot that for me. All right. It looks kind of weird right there. What happens at 0, though? It looks like it approaches 1, according to this. Okay, fine. Whatever. And this is actually equals 1 for some reason in C. Right? Just don't do it. Right? Weird things happen. Sometimes when you... so, yeah, go ahead.
I just have a question, kind of referring back to the integer part at the top.
Sure.
What would happen if you just, from the beginning, just made everything a double?
Then you would take up way more memory than you need. So what would happen if you did everything as a double? You'd take up more memory than you need. You just also shoot yourself in the foot eventually. Because here's another one. Let's see. What happens when you take 1.0 divided by 3.0? What's that going to be equal to? 1/3, but let's write it out as a decimal. 3333333. How many decimals of accuracy do I have? 17. Eventually, it'll get down to either 2 or 4, depending on the representation. Now, if you take that same number and you add it to itself 3 times, are you going to get 1? Nope, because there's a little tiny error at the end. Right? So, when you need exactitude, when you need exact numbers, use integers. Things that are integers should be integers. Things that are doubles, floating point numbers, should be doubles. Right? So, and then I'll put question mark here, right? 2 or 4, right? Something like that, right? You only have a certain amount of representation there. When using the math library, you may need to provide GCC with some additional flags. Right? For example, GCC hyphen LM, foo.c hyphen LM, right? There we go. Hyphen L means link in, and M means the math library. Right? So if you're using something in the math library, more than likely it's going to say, I don't know where the math library is. And so I'm going to tell it, well, link into the math library wherever it happens to be on the system. This may or may not be required. It depends on your setup. I think it might be required. I think I might have changed my setup. Let's find out though. Let's go ahead and try to take the square root. Double y is equal to square root of c. All right, and so that would be square root of 1/2. I have no idea what that would be, but let's find out what it is. So y is equal to y. There we go. All right. And let me clear this out. GCC demo.c. There we go. Wait, well, first of all, what should I have done up here? I didn't include it at all. Include what? Math.h. There. Now let's clear this out, and let's see if GCC is okay with this. No, it's not. Wait, square root, I have no idea what that is. So once again, if you're going to use your rubber duck debugger here, then go ahead, right? Hopefully it'll, what does this error mean? Right? And I'll just cut and paste it there. There we go. Indicates that the linker cannot find the definition of the square root function. And see, it's part of the math library. So you need to link in this library when compiling it. Do you remember how to link in the math library when compiling your code? Well, do you remember I put it in the notes just now? It's what? -lm, right? But let's ask it. Is it -lm? Yes, that's correct. Thank you. I got it. Yay. Now it runs. So what is the square root of 0.5? Apparently it's 0.7 something. Okay. So sometimes you might need to link in the math library if you're using math stuff. All right. That's variables and operations. Now we need to do input and output. First of all, we've already got some familiarity with output, right? You use printf. Printf can be used to print a formatted output, right? That's what the F stands for. It's formatting. The formatting that we use are what are called placeholders, right? You provide a string, you can put whatever you want in that string, but if you want to print the value of a variable into that string, you use a formatting string. You use %f to do a double, right? Don't ask me why. It should be D, right? Because it's a double. Well, it's F for floating point numbers, right? And it'll default to 6 decimals of accuracy. F is for floats, floating point numbers. Right? What if you wanted to do an integer? You'd use %d, which is what the double should have been, but that formats an integer. It should have been I, right? But I is used for something else entirely, right? What if you wanted to do a single character? This is the only one that makes sense, so I'll let you guess. %c, right? Formats a single char, right? When you use those in your string, because they all begin with a %sign, C will look at that and say, I'm not going to output %f. I'm going to replace that with whatever variable you give me. You can provide as many placeholders as you want in the string, but the order matters, right? If you have, say, 3, and we'll do this here in a second, if we have 3 placeholders, then the first variable corresponds to the first placeholder, second one to the second, and the third one to the third one, right? Let's come over here and do it. I'll go ahead and preserve. Let me change it to 42. 42, there's A. Let's do a double as well. Double B is equal to 3.5, right? And char initial is equal to my initial C. Right? Now let's use printf to print all of these out. Printf. A is equal to %. What do I use for a placeholder for an integer? D, right? B is equal to, what's the placeholder for a floating point number, a double? %f. And finally, my initial is %c, right? And let's end the line. Right? You can put whatever you want in here. If you want to tab over, if you want a bunch of spaces, if you just want to say hello, all right? You can put whatever you want in there. But if I don't specify the variables, then first of all, GCC is going to complain about this. I'm no longer using math. It's going to complain that, wait, there's no variable for the first one. There's no variable for the second one. There's no variable for the third one. These were just warnings. If you want to shoot yourself in the foot, go ahead and do it. That's what C is saying. But I'm warning you about it. What happens when we actually run this thing? Well, I'm not specifying what the variables are that are going to be printed, so what gets printed? Garbage. 0. This non-printable character here. Remember I told you the ASCII text table, right? It has some things that are non-printable, like the bell or the line feed, right? The carriage return, stuff like that. That's what it's printing, something there, and that's why it's a question mark. I have no idea what this is, right? So let's come back over here and fix what it's warning us about. A, B, and initial. Because A is going to correspond to the first placeholder, B is going to correspond to the second placeholder, and initial is going to correspond to the third placeholder. Now I will get some sensible output here. Right? 2, 3.5, and C. Okay? C will warn you about it if you have the wrong number. Again, that you're going to get that warning, but it's going to allow you to do it. There's a warning, and there's the consequences of that warning. In this case, it was printing out nothing. I don't know. It's just whatever was stored in that memory address when it was compiled and ran. Right? So there are your 3 placeholders. Right? All right. Yeah. See, there's code. All right. You can also use modifiers. Modifiers to specify more digits of accuracy. Right? So for this, I'm just going to go ahead and go back over here and do another demonstration. I don't need to create my own pi because math already has pi. I want to print out m_pi. So let's do that. Printf. Pi is equal to %f for a floating point number and end the line, and then m_pi. There. Now, as I said before, GCC a.out, it's going to default to, sorry, get over here, there we go. It's going to default to 6 decimals of accuracy. 14159, 3? Is that correct, actually? Does anybody know the pi out to 6 decimal places? 27, I think it is, right? Yeah, something like that. So this is not correct. Let's do some more let's go with 7 decimals of accuracy here, right? And it turns out that it was wrong. I mean, it wasn't wrong. Just what was it doing? It was rounding. It doesn't change pi. Remember, you can't change pi. That was a preprocessor directive. You'd actually have to go to the math library and rewrite the math library to change what pi is. All it's doing is, for the purposes of printing, it's printing out a modified, rounded version of it. Let's go with more digits. More sig figs here. Let's go with 16. Is that going to be accurate? Should be. Why? Because including the 3, that's 17 digits. What if I went out even further, though? Let's go 25 digits. Or 25 digits. Yeah, I don't know. I don't know. Let's ask. Pi to 25 digits. There we go. All right, let's go ahead and grab that and do a comparison over here. All right, there's a comparison, and then there's the other comparison, and I'm just going to line them up. There we go. There. So, was it accurate? Nope, not at all, right? That's because you only have 17 digits of accuracy here. Well, you can go ahead and print 25. Yeah, go ahead. Garbage. Whatever is stored in memory. Let's go ahead and go 255. Maybe it it goes to zeros eventually. Yeah.
Wouldn't it actually be because of how a binary works and how it can only go to like pads and pads?
Something, yeah. I mean, there are things that aren't going to be representable. Like 1/3 is not representable in binary. That's why you get this, right? And so it's coming up with these numbers somewhere in order to print it, but it's probably just grabbing random memory garbage.
I thought it was probably calculating out.
Oh no! It's not doing that. No. It's only going to do exactly what you tell it to do. Yeah.
Could you print the first 17 and then starting again, like start at the next digit and print that continually for the next 17?
No, it's not gonna compute it for you like that.
Like, say you want to start by it, 10 digit.
You could start in the middle somewhere, like you could start at 9 and then print out the rest of this, but that goes beyond the scope of what we're doing here. You'd have to put that into a string, which we'll talk about later, and then you'd have to take a substring. It's not at all easy to do that. But you can do other things like, say, pad things out. Let me go ahead and go with an int. I'll go with pi still. Printf, pi is equal to, I'll put in another number here. First of all, let's go ahead and kick it down, back down to only 7. But what I'll do is I'll say 20 in front of it. So that's 20.7. Now what that's going to do is it's going to print it out to 7 decimals of accuracy. But also it's going to print out a bunch of leading white space. That allows you to align things. I didn't put in a nice end-line character there. Let's go ahead and get rid of the 255. Right. That's just dumb, right? There we go. Now what happened here? 7 digits of accuracy, if you counted those, 1415927. 1 column here for the period, for the decimal place, and then another column here for 3. In total, that's going to be 7 plus 1 plus 1, that's going to be 9. I said I wanted 20 columns of data. So guess how many columns it padded it out with spaces? By my math, it'd be 11, right? Because we did 9, here 9, right? How many spaces are in front of it? Well, I said a minimum of 20, so what's the remainder? 11? Right? I did it right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. There we go. If I wanted this printed out to, say, I don't know, 3 decimals of accuracy, and then 15 columns minimum. Oops, 15 columns minimum. There we go. Then I'm going to have 1, 2, 3 decimals of accuracy, plus 3 and the period for the full number, so 5 total, meaning that how many spaces are there now? 10. Right? You can do the same thing with integers. Int x is equal to, I'm not going to call anybody out on their NUID, but some of you have NUIDs that begin with a 0, right? So what if you wanted to print it out with that leading 0? Can I write this, by the way? Can I write 0? Well, yeah, but what happens? It's going to ignore leading zeros. But when you actually wanted to print out your NUID, right, you don't want it to be like that. You want it to look like, well, here, let's see what it looks like first. Oop, that's int x. What? All right, what's wrong? Okay, it's not. My typing is quicker than my connection to wherever it's going. So there we go. All right. So does that look like an NUID to you? No, there should be a leading 0 there. So what I can say is I want at least 8 columns of data here. Well, that's fine, but it only gives me a space. I actually want a 0 instead. GCC this, run it, and there, now you're getting your leading 0. Right? If you wanted 200 leading zeros, you could do something like that, but that's a bad idea. Right. Let's go back to 8. All right. There are lots of little tricks like this. And it's valuable to learn not only because you're going to be doing standard output and just make it look nice. You don't have to format everything exactly like we do. Later on, when you have formatted output, what the grader will do is it'll actually look for key values, right? So if you output 1.5 and then 5 spaces, we're not going to say, okay, you fail because we expected 1.5 and 4 spaces, right? We're looking for that 1.5, right? Later on, when you do more complex programs and you do output, the output has to be readable, right? That's what we're looking for. The grader has been set up to be smart enough to ignore variations in formatting output, okay? But those are ways that you can do it. And also another reason that you'd want to learn something like this is because every single programming language that I'm aware of supports printf style formatting. Most of them have a printf function. Guess what? They just reuse the C function. Or something like Python doesn't have a printf function, but they have formatted strings, and they use a very, very similar convention. Right? So this is a tool that you will be able to carry over into most other programming languages. Right? Make things look nice. If you're an actuarial and you want to produce a nice-looking table, right, then you would do something like that. And once again, those are their examples. Let's come back up here. The general form is x.yf, where x is the minimum number of columns to print, and y is the number of decimals of accuracy to print. Right. With our few remaining minutes here, let's quickly just introduce input. So standard input, the standard output, by the way, is your terminal, right, or your console, or whatever, right? The standard input is done with interactive programs, meaning that somebody is sitting there, like this this mild converter here. Somebody is sitting there and it prompts you for input. Somebody mashes the keyboard as input, and then it takes that input and processes it, right? That's interactive programs. We're going to talk about it very briefly here at the start of the course, and you're going to do some of it, but we're very, very quickly going to get away from interactive input because the vast majority of software is not written for some human schlub to sit there and do stuff, right? The vast majority of software is written to automate things. And so therefore, the vast majority of software is written to interact with other software, non-interactive input. That's the whole reason to write software, so we don't have to do things. Yeah.
When you have that percent sign x dot y at x is the minimum number of
Of columns to print. Yep. And since it's always everything in computer science worthwhile is monotyped, right? Every letter takes up one column, right? Everything over here this is not monotyped because the DO here is a lot longer than the TO down here. It's called kerning. That's because the D is much larger, but there's also kerning here where letters get shoved together to make it look nicer. That does not happen in monotyped fonts. Right? Okay. All right. So the standard input, we use scanf. That's the opposite of printf. Just very, very briefly here, what we're doing is we're reading. We still have the same formatting here. It's going to be percent and then something. And then we have the variable that we're going to read stuff into, but we always put an ampersand in front of it. For now, it's magic. If you want a preview of something that we're going to be doing in, say, week 8 or 9, that's pointers. And the percent sign, the ampersand there, is giving you the memory address of that variable so that it can do what's called pass by reference, right? Again, don't worry about it. Just know that if you left it off, GCC mile converter, right? It's going to be a warning. LF expects an argument. What are you sure you meant this? Right? And then I'm sure that if I asked the rubber duck over here, it would say, well, that's wrong. And then ask it, well, how can I fix it? It'd say, put an ampersand in front of it. Just for now, remember that the ampersand is magic. But at the end of the day, it's very brittle, very limited. We're going to get away from this as quickly as we can. But for now, this is going to be our way of doing input. Right? The only difference between printf and scanf is with doubles. Scanf, you use the same placeholders, except for doubles, you use %lf and f instead of f. Sorry. Right? The reason you use LF is that L stands for long. It's a long float. It's it's telling you that it's telling scanf to expect a 64-bit number rather than a 32-bit number. Right? And then finally, when using scanf, always remember to use the ampersand in front of a variable. Again, magic for now. Magic for now. We'll talk about it later, though. Right? On Wednesday, we'll pick it up there with more examples before we move on to the non-interactive input. Like I said, we're going to get away from this almost immediately. Right? Any questions? Otherwise, remember, no class on Monday, as well as no help sessions on Monday.